it gives us the Q3 heap.java. We need to try to convert it to something like a binary tree. So this is your heap entry. Originally, our heap is in an array, okay? It's in an array form. We want to try to convert this become into a real tree. Okay? This is our original tree. 11, 5, 3, 4, 11, 5, 8, 3, 4. Let's say we add number 15. If we want to add number 15, right, what we do is we add it in the end of the array cell, okay? So we add it in the end of the position here. And then later, we perform a trickle up, okay? We want to check whether we need to move up, okay? So we perform a trickle up like this. So far, is this okay? Let me use a blue color. Blue color means this is our final example. I'm considering one thing. If my tree is expand infinitely, okay? If my tree need to expand infinitely, I am planning, okay? I am planning. So in my class, right, okay? In my class, I need a probably tail variable, okay? I need a tail variable to tell me I'm at which address, so that when I want to perform inserting, I know You know why we need to do it in tail? Because when we insert it in our heap, right, we always insert it to the tail one. Then only we trickle up. Then only we trickle up. That's why we need to have a tail in our class. If we use a tree structure, I need to have an indicator. Who is my tail? Let's say if this is my tail, okay, my current tail is this one. Let's say I want to insert a new, okay, I want to insert a new B. If I want to insert a B, right, so I know I can go to this branch, or I can go to this branch and then insert the new B. Then only I perform a trickle up. Makes sense. So if I want to perform a trickle up, right, I need to know the parent. I need to know the parent of I need to know the parent of 11, correct or not? If I need to know the parent, right, so I need to design, okay, I need to design this class. Let's say I insert the B. The B is green color, okay, the B is green color. So this one we highlight B. The value is, let's say 15, okay, here add 15, okay. When I insert B, right, okay, when I insert B, let's say this is 15 now, okay, this is 15. I need to, okay, I need to compare it with the parent, okay. I need to compare it with parent. Who is the parent of B, okay? How can we know it? How do we know who is the parent of B? When you perform a trickle up, right, you need to use the parent index. This is an array, okay? This is the array. But we are not doing an array anymore, okay? We are not doing an array anymore. If you want to know who is the parent, okay? If I add 15, right? If I use this formula, okay? If I use this formula, I know, okay? I know add is the parent. I know add is the parent. But, okay? But in this situation, okay? In this situation, we are not doing an array anymore. We need to do it like a tree, okay? I need to do it like a tree. How do I know, okay? How do I know who is the parent of the B? It's not an array. We convert this to a tree. We convert this to a tree. This is a tree already, like binary search tree. I will store a parent class field. So my parent class field, I will store A, okay? I will store A. So I just use 15. When I look at 15, right, I just check with A. I just check with A. So I know whether we need to perform swapping or not, like this. Get the class field, okay? The parent. The parent or the data type. The data type is also a heap entry. The parent class field, the on data type. It is the on data type. So I will store my parent in here. So I check with my on parent. I check with the parent. So B check with A, okay? B check with A. So B check with A. Is it needed for swapping? So like this, B, okay, B check with A. B check with A like this, because because I do not want to iterate from the head. I don't want to iterate from the root. Okay, I don't want to iterate from the root to find who is the parent of B. So let's go and modify our heap entry. Our heap entry, like, got a priority. Okay, priority. The priority is also known as the value. Okay, it's now also known as the value. VALU. In this diagram, I shouldn't write value. No. This is very confusing because the object is value also. No. Let's just call it priority. Okay, priority. Okay, this is priority. That is our priority. So in our heap entry, okay, in our heap entry, my Q3 heap, right, we store the tail address. And one more question, okay, one more question. When we perform trickle up, right, okay, when we perform the trickle up, if you look at the formula, okay, if you look at the formula, what is the stopping condition? Our trickle up stopping condition when the index is more than 0, okay, when the index is more than 0, then we stop. That means, okay, right, we need to stop when we reach the head, okay? We need to stop when we reach the head. So that means, right, okay? That means I also need a head pass field. Do you agree? So that I know when to stop when I perform a trickle up. We need a heap entry of tail and also the head, okay? To store the address, okay? We need to store the address of the current head and the current tail. So let us design our heap entry, okay? By the way, all this needs to be private. We need to add a private keyword. We need to add a private keyword. And also in our heap entry, okay? In our heap entry, we need to store the parent, okay? So private heap entry also, okay? Private heap entry. So we have a private heap entry of the parent, okay? We want to know who is the parent. Heap entry need to have a left branch to store the next value, okay? Example, this one, okay? We need to store the left branch. This one, we need to have a right branch also. What is the data type? What is the data type of the left branch and right branch? Data type is also heap entry. So heap entry of left and right, okay? This is the branch, okay? So when we construct our heap entry, right, we take in a priority and we take in a value. Then we need to also initialize, okay? We need to initialize who is the parent, okay? So let's pass in the parent, okay? Let's pass in the parent. So it's going to be look something like this. We pass in the parent, priority, and the value. So this one is actually, the naming is very bad, okay? This one is in parent, okay? This is the in parent. So parent, okay? Parent is equal to in parent like this, okay? And also we need to initialize that, okay? We need to initialize left branch to become null, okay? Our left branch is equal to null. And also our right branch, we initialize it become null, okay? With this we are done. And then this is get priority, this is get value. This is the default one, okay? This is the default one, so I don't touch it. So far our heap entry is completed. And our current DSA heap entry, right? We need to convert this, okay? We need to convert this. This is no longer needed, okay? This is no longer needed. We need to remove this one, okay? We need to remove this one. And we probably need to maintain the count. We can also maintain the max size if we wish, okay? If we wish. So let's just look at the constructor, okay? Let's just look at the constructor. Q3 heap is equal to new heap entry, okay? We don't need this one anymore, okay? We don't want this one anymore. So when we start our Q3 heap, we just initialize the count is equal to 0. So when we add, okay, when we add, we take in a priority and we take in a value, okay? I know you roughly don't have the idea yet, or probably you got. When we add, right, initially, okay, you tell me, I initialize my head, forgot to initialize the head and tail, okay? We need to initialize the head and tail. Let me move this, let me group it together. We need to initialize the head, we need to initialize the tail. So our Q3 heap, we need to set up head, okay? Initially, okay, initially. We don't have any head, okay? Initially the tree is empty, okay? Initially the tree is empty. So head is equal to null, okay? We initialize head is equal to null and we initialize the tail, okay? We initialize the tail as null, okay? This is the first one Q3 heap. When we perform adding, okay? When we perform adding, right? We start looking at the code, okay? We start looking at the code. Can you tell me what is the first thing you need to do? Okay, we need to check head only. No need check the tail, okay? No need check the tail. Because initially it's empty, okay? Initially it's empty. So we need to check if our head is equal to null. Do you agree? There are two conditions, okay? There are two conditions. If, okay? If our entire tree is empty. If our head is equal to null, then we need to initialize the head, okay? Head is equal to what? If you plan to implement the max capacity, okay? If you plan to implement the max capacity, you also need to add one more checking, okay? Count less than max capacity suppose in the outermost if statement. So if our count is less than our max capacity, what is the constant name? Max size, okay? If our count is less than our max size, then only we want to perform all the things inside here. This one is removed like this. If our head is equal to null, we need to, if our count is less than our max size, okay? If our count is less than our max size, we can make a new heap entry. Heap entry new child is equal to new heap entry of, we don't have a head right now, okay? We don't have a head. So I'm going to say as now head and then a priority and a value, okay? Here's like this. So our head, okay, our head is the new child, like this. How about our tail? What is our tail? Our tail is also the new child, like this. Else, okay, else if our head is not equal to null, what should we do? Else if our head is not equal to null, that means, okay, that means our tree have item, okay? our 3F item. If our 3F item, right, what should we do inside the else scope? First, we just need to add, okay? We just need to add to the tail. First step is add to the tail if it's not empty. Do you agree? If our tree is not empty, right, we add it to the tail. Or let's say this tail is equal to A, okay? Let's say this tail is equal to A. Then we add it to the tail. We also have a new child, but this time, okay, this time, right, our parent, okay? This time our parent, what is our parent right now? Who is the parent of this new child? Think carefully. Who is the parent of this new child? Look at this diagram. Look at this diagram. Who is the parent of this B? By the way, this when I insert, okay, when I insert here, okay, let's look at here. Okay, let's say I add 15. Let's say I add 15. If I add 15, okay, I add 15 here. Who is my parent? Who is my parent? A. Then what should be put in here? Who is the parent? Yes, exactly. It's the tail. Okay, it's the tail. So this is our new child. Our new child currently we store the parent. Okay, we store the parent and we store the priority. We store the value. Okay. Afterwards, okay, afterwards, right? There is one more problem. Okay, there is one more problem. Now we want to insert it to the parent. Okay, we want to insert it to the parent. There is possibility. There is a left branch. There is a right branch. How do we know we want to insert left branch or right branch? When we insert heap, right, okay, when we insert heap, we need to always insert to the empty area first. Okay, we always need to insert to the empty area first. So left, then only right. Left, only right. Okay, doesn't matter. Doesn't matter the child is larger than this or not. It's always insert to the left branch first, then only to the right branch. Look at this diagram. Okay, look at this diagram. We don't care. Okay, we don't care 15 is larger than 8. Okay, when I insert 15, right, okay, when I insert 15, we don't care 15 is larger than 8 because in our array just now, okay, in our array just now, yes, we always insert to the empty. Okay, we always insert to the empty element. Okay, we always insert to the empty element first. If we insert to the empty element first, right, that means, okay, that means we are inserting to the left branch. Do you understand this part? This is very important part. We always insert to the left branch first. Okay, we always insert to the left branch. Doesn't matter 15 is larger than 8. Doesn't matter 15 is larger than 8. We always insert to the left branch. Can you understand? Start from the left branch if it's available. Okay, now you tell me what should you do inside here. Okay, so what I will do is I will do it inside my heap entry. Okay, so let's write a public method. Okay, public method. Okay, public, let's say void. Okay, public void. Let's say call it as set child. Okay, let's set child. Okay, set child. So we get our heap entry. Okay, heap entry of the child. So I will write a setter. Okay, I will write a setter. So if, okay, if our left, okay, if our left is equal to null, so what should we do? We need to, tell me, insert. Exactly. So our left is equal to the child. Okay, else what should we do? Exactly. This is the beautiful part about object-oriented programming. Okay, object-oriented programming allows us to group it together. Okay, we group the relevant function. We group the relevant function to a class. Okay, we group the relevant function to the class that makes this object-oriented programming very beautiful. I will tell you to set child the new child. If it's not empty, okay, if it's not empty, right, we need to, after adding, okay, after adding, we need to perform a trickle up. Okay, we need to perform a trickle up. Okay, we need to perform a trickle up. So this trickle up, right, will not longer tag in the index anymore. Okay, we need to modify this. So this trickle up, right, will have the parent index. Okay, this is the code of the trickle up. So, okay, so this is the current index convert. It become our heap entry. Okay, so this is our heap entry. Okay, heap entry of the current node. Okay, it will be no longer called as current node index. So it will just call as current node only. So our heap entry, okay, our heap entry of the parent node is equal to, I want to trickle up this new child. Okay, I want to trickle up this new child. How do I get this parent? How do I get this parent? So we call the current node parent like this one, although it's private because it's the inner class. Okay, you can call it like this. This is the stopping condition of the recursive. If our current node index more than 0, okay, if our current node index more than 0 means if we are not head yet, okay, if we are not at the top, okay, if we are not at the root, okay, this is the root, this is the root, okay, this is the root, this is the leaf. If our current node not equal to our head, okay, then only we want to perform the if statement in here, okay? So this heap current node index, okay? This heap of the current node index is just simply current node, okay? This is simply a current node, okay? If our current node get priority is more than our parent node, okay? If it's more than our parent node priority, okay? This is perform the swapping. So B and the parent need to swap position, and then we trigger up the parent, add a command, okay? Add a command. If you look like this, you try to convert it to tree, okay? It's very hard to understand, okay? It's very hard to understand. Huh? How can I convert array element? How I convert array element to do swapping? Don't look at it. Okay, don't look at it. Look at this command only. Okay, look at this command only. The child need to swap position with the parent. Let's look at how to we delete. When we perform delete of maximum heap, okay? If we perform delete of maximum heap, right, we actually remove the first item. Okay? We remove the first item. Maximum heap. That means, okay, this one is essentially what? This is the head. Okay? This is the head. Okay? This is just the head. Okay? We remove the head. Okay? We remove the head. After we remove the head, okay, right, then we trickle down. When we remove 11, okay, when we remove 11, right, so this would remove, okay, this would remove to the top, and then there is a violation, okay, this is the violation. Since f is greater than 4, okay, our highest value always need to be at the top. When we perform a remove, right, we need to return the value.